Good evening to one and all present here. Hope you all are safe and sound. On behalf of Ayyer panel of students, I welcome all participants to the fifth day of the Mathematics Online. I have great pleasure in welcoming today's speaker, Professor Arvind Ayyer, to this platform. Professor Ayyer obtained his MSc degree in physics from IIT Kanpur and was awarded his PhD in physics from Rutgers University. Indian Academy of Sciences and is currently an associate editor for Indian Journal of Pure and Applied Mathematics. He is also an editorial board member for algebraic combinatorics. His areas of specialization include probability theory, combinatorics, and statistical physics. He is currently an associate professor of mathematics at ISC Bangalore. With great honor, I welcome the professor to enlighten us on the mathematics of time. Before we begin, I request all participants to keep their mics muted unless any questions, in which case they may unmute themselves and ask or type them in the chat. Sir?
Hi, can I start?
Yes, sir.
Okay. So hello everyone. Welcome to this session. I guess I'll start sharing. So can you see this?
Yes, sir.
Okay. So one of the disadvantages of an online lecture is, of course, that you can't meet anybody and you can't discuss. But on the other hand, one of the few advantages is I can have my coffee while giving my seminar. So I want to talk about the mathematics of tilings, and I want to make this talk a little interactive. So I will at the proper times ask you some questions and ask you to answer. And of course, please do interrupt me if you have any questions. Okay. So I want to introduce a branch of mathematics related to tilings, which has connections to various other branches of mathematics. So before we begin, we need to make sure our terminology is clear and the kinds of questions we are going to focus on. Oops. Yeah. So here's a rough outline. So here's a tiling problem that someone could give you in principle. Here is a region, this funny looking non-convex region, polygon, and here are some funny looking tiles. Okay, and I ask you, find a way to tile this region with these tiles. What does that mean? It means each point in this space must be covered by exactly one of these tiles. And yeah, so no point should be left uncovered, and every single point should belong to exactly one tile. I mean, don't worry so much about the boundaries. So if a point is there on the boundary of two tiles, then one can make some convention, but don't worry about that for now. So, but here's the question, and you know, if I give you...
So, can I tell this?
Yes?
How to tile?
No, yeah, so I was going to say, so if I give you enough time and I walk away from here and give you the rest of the afternoon, I'm sure you'll be able to tile it, and here is one solution. Okay? So this is the kind of recreational problem you might have seen in some magazines, but I claim this is not a mathematically interesting problem. Okay? This is why? This is some random shape. These are some random tiles. I mean, why should any of us or you waste your time trying to solve this problem? I mean, of course, you're bored. If you're bored and you have nothing better to do, sure, go ahead. But why should we spend our times on this problem? So the main reason this is not a good problem is that it's poorly motivated. Why should you study such a problem? there is nothing particularly interesting in the shape, in the number or size of the tiles, in anything particular. So I would claim this is not an interesting problem. But there are interesting problems, and I'm going to come to that in a second. So here are some general notions. You have a region and a set of tiles in a tiling problem. You are asked to cover the regions using those tiles. Depending on the nature of the problem, either exactly once or multiple times, both are okay. But you should not have any overlap. And you are allowed to certainly translate the tiles, and in some problems even allowed to rotate them, but nothing else. You cannot cut the tiles, or you cannot reflect the tiles about any axis. Right? These are the general notions. Now, what are the questions one can ask? First question one can ask, if I give you such a region and a bunch of tiles, is does the tiling exist? If no tiling seems to exist, so you played around with it, with the problem, and you worked hard and you can't seem to find any tiling, can you prove rigorously that there is no tiling? So by prove, I really mean prove, rigorously prove. On the other hand, suppose there is one. If there is one, then there in principle can be many, and the question is, can you count exactly how many there are? In many problems, it's difficult to say exactly how many, but maybe you can say how many are there approximately. Can you give some approximate count? This is more relevant when you have families of regions, as you will see very soon. Can you construct an explicit example? In many cases, it's if the region is very large, then you might want to start with an explicit example. And this is related to this question in a way. I'll explain. If your region has special symmetries, can you find tilings with those symmetries? And if there are symmetric tilings, can you count how many there are? And then, now suppose there are a large number of tilings, can you generate a random tiling? Uniformly random tiling, that is, among the set of all possible tilings, pick one at random. Uniformly, I mean, each tiling is uniformly random. Each tiling is equally likely to be picked. That's what I mean by uniformly random. And can you transform any tiling from any one to any other one by some simple operations? These are the kinds of questions one can ask. Some are, of course, more important than the other. Some are more relevant in certain areas of mathematics, and I'll describe all of that. So let me start with the following example. You all know what chess is. So I have an 8x8 chessboard, and I remove 2 corner cells. Okay? But I remove which ones? 2 opposite corner ones. So this is my region. And now my tiles are what are called dominoes. You might have seen them, especially if you have pizza a lot. These are 2 adjacent squares, either adjacent horizontally or vertically. Okay? And you are allowed to use any number of either one. So you can use as many of horizontal dominoes as you want, as many vertical dominoes as you want. And the question I want to ask you, and I want you to answer, is how many tilings are there of this chessboard with 2 corners removed with dominoes? So I'll give you a minute to think. And I'll finish my coffee. Please unmute yourself. And it's okay to get the answer wrong. I mean, it's not a trivial problem. Okay, I finished my coffee. Maybe I'll give you a hint. So suppose I was instead looking at the whole chessboard. Suppose I did not remove these 2 corner cells. Okay? Then this is clearly an unfair question. it is not fair of me to ask you that question because the number is going to be incredibly large. And I cannot expect you to do some back of the envelope calculation and tell me the answer in a minute. Right? So that would have been an unfair question to put the entire chessboard. So that's a hint. Okay.
So no tiling exists.
Very good. Yes. Who is E2? Imon. Yes. Very good. That's right. Why? Okay. Very good. That's absolutely
So
right. So,
as
so
usual, we
yeah.
color that.
Just a second. Before you answer, let me give the others a hint, and maybe now
Yeah,
they
I
can
also
see.
by
So the hint is that a chessboard is not a proper chessboard until all the cells are colored black and white. So here is a chessboard where the two opposite corners are removed, where the black, you can see the black and white cells, well in this case gray and white. And now can you see why Imon is correct?
yeah.
Yes, sir.
Yeah. So Imon, why don't you explain to everybody what the logic is?
So every regardless of where it is placed, the dominoes, if we color that black and white, so it will cover one black, and so there will be at least 31 black squares and 31 white squares. It should have been, if it was a proper, if a tiling would have existed. But
That's
here
right.
we can see
Every
there,
domino covers exactly one black and one white cell. Exactly. Go ahead.
but here we can see there are 30 white squares and 32 black squares. So this is not going to happen. So that is why.
Correct. Very good. So, and that is why it would have been unfair if I put both these corner cells back as in the original chessboard, because then there are exactly 32 black and 32 white squares, and then the number will be actually quite huge, quite large, and actually I will be able to give you an answer for that in the rest of the talk. But yeah, this is an example of a coloring argument. So this is a purely combinatorial argument which allows you to prove without any doubt that there cannot be a tiling. I mean, you can struggle forever. You can maybe manage to put 30 dominoes, but then the last two will be black and then there's no way you can come. Okay, so now let's come to again domino. So now for a while we will talk about domino tiling. So dominoes are as before these kinds of tiles covering having area 2. So now here is a question. You have a 1 by n rectangle, okay, like so, and with n equal to 5. And now my question to you is, how many tilings are there of the 1 by n rectangle? In general, here is n equal to 5, but if you can give me the answer for general n, that would be.
So I
Sorry?
think,
Yes, P2 was.
sir, the tiles are
Part.
considered, all the dominoes will be considered same, right?
Yes, all the dominoes are same. Yes, they are
Yes, sir.
indistinguishable.
So then if n is odd, then it will be 0, I think. And if n is even, then 1.
That's right. Yes, path is exactly right. So if n is odd, like this example here, there is no domino tiling because there are 5 cells and each domino covers 2 cells. So unless the number of cells is even, you cannot possibly hope to have a domino. So if you try in the brute force greedy algorithm way, you put a domino in the first 2 cells, then you put a domino in the next 2 cells, and then you are left with this empty cell. What the hell are you going to do? You cannot cover a single cell with a domino unless you have overlaps, which is not allowed either. So the answer, as Path said, is 1 if n is even and 0 if n is odd. So this was simple. Everybody is on board? If there are any questions, please ask. Okay, let's up the ante a little. Now I give you 2 by n rectangles. Okay, and still I am asking for domino tiling. So 2 by n means, by definition, there are 2n cells, which is always an even number, so the parity argument cannot work. And so in this case, let me ask you, for any n, can you construct an explicit domino tiling? Somebody?
Yes.
Yeah.
Huh. Tell me.
So by just placing vertical dominoes.
That's correct. Yes, I should have asked Shaurya maybe. Okay, yes, the path is right. Maybe that's what you were also going to say. Yes, you can just put vertical dominoes, any number. If you have 2 by n, you put n vertical dominoes and you're done. So I hope everybody sees that. That is one. But now that is not going to help. Okay, now I am going to ask you to tell me exactly how many there are. So this is not a trick question anymore. Yes, Shaurya?
It's going to be Fn.
What is Fn?
Nth Fibonacci number.
Very good. Yes, that's exactly right. How do you see that?
We could form a recurrence here.
Yes.
Say we have a 2 by n rectangle that you have to tile. Now
Yeah,
consider
let's say this is 2 by n.
Yeah, so consider the first, like the top left square.
This one, yes.
Yeah, if it's tiled by a vertical tile, then
yes.
The number, like there are, like say an denotes the number of ways to tile a 2 by n
Yes.
rectangle, then there are n minus 1 ways to tile the rest of the thing.
Perfect.
And if you have a horizontal thing, then you'll have to have a horizontal thing below that also, and then there'll be an minus 2 ways to tile the remaining things. So we'll have an is equal to an minus 1 plus an minus 2.
Very good. That's correct. So the recurrence is exactly right, and the answer coincidentally turns out to be right, because you are not exactly correct because you did not check the initial conditions. So it turns out that the number is Fn plus 1, the n plus 1 is Fibonacci number, because for n equals 1, it is 1. So okay, so let me say this. So the standard way of or by now the accepted way of defining the Fibonacci numbers is with the initial conditions f0 is 0 and f1 is 1. So f2 is also 1. But here you will, if you take the 2 by 2 rectangle, you have 2 ways. So that's actually f3. So it's actually, it's fn plus 1. Okay? Yeah, but you're absolutely right. That's exactly the argument. So here you get the Fibonacci recurrence and also the shifted Fibonacci initial conditions, and so this turns out to be Fn plus 1. Okay, I hope everybody understood that argument. Unmute yourselves. Okay. All right. So now let's go to an even harder problem. Now let's look at general 2m by 2n rectangles. Okay, so this is now like the chessboard example, which, as I told you, is an unfair question, the full chessboard. So you want to count the number of tilings, let's say f2m to n of the 2m by 2n rectangles with dominoes. So the question is how many? And amazingly, there is an exact answer, and it's complicated, but it is there. And again, amazingly, in the year 1961, two separate groups found the answer. They came from slightly different motivations. So both are groups of physicists, or one is a group and one is a singleton. So in Temperley and Fisher, Temperley is a probabilist, and Michael Fisher is a physicist. They published a paper, and separately, Peter Kastelein, who was a Dutch mathematical physicist, who was actually at that time, I think, working for Shell, the oil company. They showed that the number of tilings of the 2m by 2n rectangle with dominoes, so is given by this amazing product formula. So what is it? You have a power of 4 outside. Then you take the product of j going from 1 to m and k going from 1 to m, and you take cos squared of j pi by 2m plus 1 plus cos squared of k pi by 2n plus 1. And you take the product of all these things, and you get f2m. Okay, so I mean, I want you to stare at this one. I mean, this is really mind-blowing formula because I mean, you know the formula of things like cos pi by 3, cos 2 pi by 3, and so on. Those are nice, but you know, maybe some of you even know things like cos pi by 5, cos 2 pi by 5, and maybe there are a few of you who, maybe one or two of you who know what is cos pi by 7. But then I bet nobody knows what is cos pi by 23. You know, so these things are horribly irrational numbers. Okay, so each of these is a horribly irrational number. It's not square root of something, so squaring it will not make it a rational number. So you're summing two, as I said, horribly irrational numbers. You get some other horribly irrational number. You get mn of these, and you multiply all of these out, and you get a rational number, and then you multiply by 4 power mn and you get an integer. Not only do you get a rational number, you get an integer. I mean, there is no way you could expect such a thing. This is true for all m and all n. Okay, this is, I mean, completely unguessable. But these guys found this amazing formula for the number of domino tilings of 2m by 2n rectangles. So if you put m and n equal to 4, you will get the answer to this chessboard problem that I mentioned.
Sir,
Yes, I am.
how would you like go about proving such a thing?
Yeah, that's what. So, right, that's the. So I cannot describe it in this talk. It requires some machinery, but they basically were able to use linear algebra. And this is so you guys are all 9th, 10th students, or is everybody here from 9th or 10th?
8, 9, 10.
8, 9, 10. Okay, so
11
when you,
also.
sorry,
11, 12 also, I guess.
11, 12 also. Okay, so when you get into, if and when you get into a math program, you will have a course on linear algebra, which is you might have seen matrices. So linear algebra is the mathematical framework behind matrices, and there are some very clever things one can do with it, and this is one of the things. It will require way too much background to explain how they proved it, but I can tell you a little bit about their motivation. So okay, maybe I'm not doing too well with time, but maybe I'll just say quickly. So as I told you, they were physicists. So why would physicists come up? Why do physicists care about tiling with dominoes? I mean, they certainly don't. So what they were interested in is the problem of adsorption. So adsorption, as contrasted with absorption, is absorption on the surface of a solid. So if you think of a solid, something like a book, you think of molecules sitting on the surface, and so you think of a surface of a solid as a lattice like this. As a uh, as a m by n rectangle, and then you think of a molecule like oxygen. It's going to occupy two of those because it's O2. Remember, an oxygen molecule consists of two oxygen atoms. It's going to absorb like that. So it can absorb like that, and so on. And then when you put such a material outside, there are many oxygen molecules, and they're going to try to adsorb on this. And a natural question from that point of view is how many ways are there? This is just a very toy model for something that for adsorption. It's a toy model because it assumes that all of them have the same energy, but that's not true, etc., etc. So it's a very basic model, but it is interest of physicists. Okay, so as I said, this is an amazing example, and let me show you how this works for m equals 3 and n equals 2. By the way, I should have said, so I'm looking at 2m by 2n rectangles just to simplify my life. If I can't take an m by n rectangle where both m and n are odd, because this is dominoes, right? So the area must be even, so at least one of them must be even. There is also a formula for 2m comma 2n plus 1. It's slightly more complicated than this. But just to simplify life, I wrote down this formula. Okay. So here is m equals 3, n equals 2. So it's 4 by 6 rectangle. So let's do the computation. So you have 4 to the 6 times cos squared pi by 5 plus cos squared pi by 7, etc., etc. You have these 6 factors, and each one of them is some, as I said, horribly irrational number. You have 4 to the 6 outside, which is 4096, and you multiply all these out and you get exactly 281. Okay, exactly. If you do this on a computer, you will get errors because you will get maybe 281.0001 or something, but you can rest assured that it is exactly 281. And there's a proof for this. So, right. Okay, so now let's come to large examples. So now we know that for a 2m by 2n rectangle, you'll have there will be a domino tiling, and there will be many. So now let's look at a large example. So here is m equals n equals 40. So sorry, but here I mean 40 by 40 rectangle. So okay. So, and what I did here, well, all these examples, all these pictures are taken from the internet, in full disclaimer. So what is done here is that this person has taken a random tiling. That means there are many millions of such tilings. You know, you close your eyes and pick one at random. Okay, so that each one is equally likely to be picked. And now I want you to stare at this, and I want you to tell me if you can see anything particularly interesting happening anywhere. Well, it's hard to say what I mean, so maybe I'll give you an analogy with Sherlock Holmes.
There are lots of squares covered like 2 by 1, 2 by 1 together, making 2
Yeah,
by
but
2.
2 by 1 is a domino, no?
No, 2 by 1 dominoes, like either both vertical or both horizontal
Very
next to
good.
each other, creating a
That's
2 by 2 square.
Yes, that's correct. That is correct. Yes, Shaurya, thank you. That is correct. But that was not exactly the nature of the question I was asking. So let me ask it this way. So, like Sherlock Holmes, what I want you to see is that there is nothing really to be seen. So, if you look at this region, let's look at a sub-region, let's say in this top right region. And let's maybe look here, the left middle region. I mean, structurally, do you see that there is any difference between the two? I mean, of course, they are different. But I mean, in terms of, in statistically, I mean, do you think there are, for example, more horizontal tilings over here than vertical compared to here, or the other way around, or any other region of the same rough size? So I claim that all these sub-regions, large enough sub-regions, are going to look the same. Okay, that was the thrust of my question. And I hope you will agree with me that there is no I mean, there's nothing really distinguishing this region from the center or from here and so on. All of them look roughly the same. Okay, here is another nice theorem. So I think Shaurya just mentioned there are lots of 2 by 2 squares where both are horizontal and both are vertical. That in the previous example, like here, this 2 by 2 square is both horizontal, this 2 by 2 square is both vertical, like that. Now, one of the questions I told you was to get all tilings. Is there some simple way you can get all tilings? So, one of you said earlier that there is one way of tiling such a region, which is by taking all vertical dominoes, for example. M and N are even, so you can just start filling the first 2 rows with vertical dominoes, then the next 2 rows with vertical dominoes, etc., etc. You can make everybody vertical. That is certainly a possibility. Now, starting with that, can you get all tilings? So it turns out, and this is a theorem, that if you systematically turn horizontal pairs like this into vertical pairs, then you can get any tiling from any other tile. That is another beautiful theorem. And let me illustrate this in this example, in this 2x4 example. So I start with, for instance, with all the horizontal tilings. Sorry, the all horizontal tiling. I take the first two horizontal ones and I do this operation to get vertical ones. I get this tiling, the fourth one. Or I take the bottom two and I flip them and I get the second one. Right? So starting from the first, I got the second and the fourth. Now, from either the second or the fourth, I flip the remaining two horizontal and I get the fifth. Right? Or I take the middle two from the first tiling and I flip it to get the third. You see? So starting from the all horizontal, I got everybody. Not in a trivial way. I mean, to get the third one, I had to come back to the first. I mean, or in other words, to go from the second to the third, you have to first go through the first. So you might actually have to reduce the number of vertical tilings to be able to increase it later. You know? So, for example, if I want to get from the third to the fifth, I will have to first necessarily make the middle two horizontal. So I'll reduce the number of vertical tilings, and then I'll have to go to second. Right? So it's non-trivial, but it is true that it is always possible. Okay. Okay, so this is a more complicated example when I'm in a 4x4 case. So I could show you how to get from any one to any other, but I think you get the point. Okay, so the other thing I asked you is how to approximate the number. So as I said, this formula is really beautiful and highly non-trivial, but this doesn't really help me if I want to know roughly how many there are. Or how does this grow with m and n? Does it grow exponentially or polynomially or what? And what are the correct growth numbers, the terms? So one can show that now let me specialize to m equals n. So I'm looking at now the 2n by 2n rectangle or square. Then one can write the number of such tilings approximately as some constant raised to the 4n squared, where this constant can be proved to be the exponential of g by pi, where g is this famous number called Catalan's constant. So what is it? It is 1 minus 1 by 1 squared minus 1 by 3 squared plus 1 by 5 squared minus 1 by 7 squared and so on. This series, you can show that this series converges, and its value is about 0.915, and then if you take exponential of that by pi, you get this nice formula. Okay, so why did I write this formula as c to the 4n squared? Why didn't I write it as so the key point in this formula is that the n squared appears in the exponent. Right? It's something raised to the n squared. But why did I write it as c to the 4n squared? Because in a 2n by 2n square, there are 4 times n squared cells or unit squares. Okay, and so what this is saying is that if I multiply c times c times c 4n squared times, I get this number roughly when n is large, and this c in some sense represents the degree of freedom of tiling in an n by n in a 2n by 2n square, right? So this is telling you per square how much you can. It is giving you a quantitative measure per square. Okay, is that clear? Any question? I think this is a non-trivial concept. Yes, Shaurya?
So roughly it's saying that there are 1.34 ways to tile a certain square?
Yeah,
Not
well,
always,
yeah,
but
kind of. Yeah.
like due to restrictions from other places, roughly it comes out to that.
Yes. So not number of ways so much, but in a sense, okay. So yeah, so you can think of it that way. I mean, I don't want to introduce more terms, but roughly, the larger this number would have been, the easier it would have been to tile. So this number represents the ease of tiling in a sense of a square in a 2n by 2n square. I mean a larger square. Okay.
Okay, agree.
Yeah. So this number is, if I had a larger number, that means it would have been easy to tile. So another way of thinking about this is if you start to randomly put horizontal and domino tiles all over this place, then after you do a little bit, you can still fill it up somehow. If this number were very low, then you couldn't do it that. I mean, it's very constrained. You would have to do things in a much more systematic way. Okay, that's the key idea. Okay, but there is a technical name for these things, but I don't want to tell you what it is. Okay, so that was domino tilings of rectangles, and now I want to talk about domino tilings of another region of squares. These are called Aztec diamonds. Again, you might wonder, like the first silly problem, why should I care to study this problem? And you will see in a second why it is worth studying. Okay, so what is an Aztec diamond? So you take a staircase shape. So forget all these things. So you take a staircase shape. So look at the top right of this AZ3. It has one cell, then two, then three. So it's arranged like a staircase, right? And this is left justified. So first row has one cell, second row has two cells, third row has three cells, like that. AZN, you go up to n. So you have n. You have a staircase of height n, and then you reflect it about the horizontal and vertical axes. So if you reflect this thing about the vertical axis, you will get this top part, and then you reflect it about the horizontal axis, you get this. Okay, so it's a nice symmetric, fourfold symmetric object. Okay, is the construction clear? Okay. So AZ7 looks like this, and as you can imagine, it's going to start to look like a diamond as n becomes larger and larger. Okay, so I think it's easy to convince yourself that there are an even number of cells in any AZ of n. You're reflecting about the horizontal axis over here, so whatever number was here, you'll have the same number here. So there's no problem with parity, so you could potentially have a domino tile. Now you want to tile this with dominoes. So how many ways are there of tiling AZ of 1? We've already discussed it. It's 2. Both horizontal or both vertical. Here's a more non-trivial question. How many ways are there of tiling AZ of 2? So this you can work out on the, and maybe I'll give you a minute. Can someone figure out? Okay, I'll wait. If you have a guess, shout it out. I mean, it's okay to get it wrong. It's not 0, and it's not some astronomically high number like 100. Yes, someone put something in the chat. Okay, Inesh is asking what is degree of freedom. Let me come back to that later, Inesh. Let me get
10.
Sorry?
10.
10? No, that's not right. Actually, that's an overcounting. I don't know who said it, but yes, that is an overcounting.
Is it 5?
Is it 6?
No, it's not 5. It's not 6. Very good.
4.
No, it's not 4 either.
8, right? 8.
Yes, who said 8? Yes, I am, that's correct. It's exactly 8. So, so here are the 8 tilings um, for AZ of 2. Okay, and 10 was too large, so I don't know who said 10, but you probably overcounted. Right, so there is, so in this case also there is a simple tiling which is all horizontal. So you can convince yourself that this works at any row. So every row has even length actually. So you just tile it row by row, all horizontal, and you will get one tiling. So that's the first one over here. And by symmetry, therefore, you also have all vertical tiling, and so you get 2 for free. And then you actually you can also do the same domino moves that I told you about in the rectangular tiling, and you get all of them. So start from here, you get this goes to this, then you do that, you go here, etc., etc. Then anyway, you will get 8. Okay, so now I give you the formula. So somebody wrote down a program and calculated, and for n1 through 6, here is the data. So for 1 it
2
was
to the
2.
2 to the power n into n plus 1 by 2.
Right, yes, you're fast. Yes, that's right. So I was going to ask you to guess. So can you guess a formula for the number of domino tilings of AZ of n based on this table? And Imon has already answered, but if anybody else, if somebody did not hear his answer and wants to take a shot, uh,
2 to the power 2n minus 1.
sorry,
2 to the power 2n minus 1.
no. This is 2 to the, so right, so the first pattern I think everybody has noticed is that these are all powers of 2. That itself is quite amazing because there was no reason to expect such a thing. We are tiling dominoes on this on these funny regions. Why would you expect a power of 2? So that's the first pattern. There's a power of 2, and now what is the exponent? So this is 2 to the 1, 2 to the 3, but this is 2 to the 6, which is an even number, so it cannot be 2 to the 12. So so this is, so maybe I have another slide here. Yeah, so this is 2 to the 1, 3, 6, 10, 15, 21, and now you know what these numbers are. And this is exactly 2 to the n into n plus 1. Okay. Right. So amazingly, this is always a power of 2, and it's a very tractable power of 2. It's the triangular number, the nth triangle or n plus 1 triangular number. Right. So this I claim is motivation enough for you to study this problem. I mean the fact that you have such a beautiful, simple formula for the number of domino tilings for these regions, and this is for any n. Remember, this is not. You could have said 8 is a coincidence. This is 2 to the 1, 2 to the 3. Then you say, okay, maybe this is a coincidence. But then you do up to 6 and you find such a nice formula. I mean, there has to be something going on. Right? Also, this is exactly the number of subsets of a set of size n into n plus 1 by 2. But there is no simple correspondence. I cannot tell you in any obvious way how to associate a subset. For example, here I cannot tell you how to associate in any natural way the subsets of 1 through 3 with these sets. Okay, so this is a deep result. I mean, it's not. It's not like just something that you could stare at it for 2 minutes and see. Okay, so there's something really interesting going on. Okay, all right. Okay, now come back to degrees of freedom. Yes?
So is this unproved?
No, this is proved. But not so long ago. So this was proved in the early 90s. So it was not like some 19th century fact. Okay. Okay, so now let me come back to the degrees of freedom, and maybe I'll also repeat, maybe that will also answer Inesh's question. So the degree of freedom, so let me do the computation here for degrees of freedom. How many squares are there in AZ of n? I told you there are an even number of squares. If you just calculate for the, you get 2 plus 4 up to 2n up to the center, and then you double it. So this is, you do the sum, it's 2n into n plus 1. So now the number of tilings is some number c, this is a different c than the previous one, raised to the number of squares, which is 2n into n plus 1. But we also already know the answer exactly this time. There is no approximation here. For any n, we are interested in large n, but for any n, this c to the this is equal to 2 to the n plus 1 by 2. And therefore, just by comparing, c is 2 to the 1/4, which is approximately 1.189. And I remind you that for the square, it's about 1.339, which is smaller. So, as I was explaining earlier, the degree of freedom is per square, because I'm raising here to the power 2n and n plus 1 because that's exactly the number of squares in my acidic diamond of size n. And what is that constant c? So the number of tilings is c times c times c times c, number of squares times, and that c is 2 to the 1/4 in this case. So it tells you the ease of tiling, and this is smaller. Therefore, this is harder to tile than the square. Okay, I claim. So there is some rigidity here. If you take this AZ of 7 and start to put dominoes randomly, you will sometimes get stuck. Okay, and I'm going to illustrate that soon, but let me give an example. Let me do it over here in AZ3. Suppose I tile this horizontally. Suppose I tile these two cells with a horizontal domino. Then you see that immediately forces this, and it also forces this. Oh, sorry, it only forces this. I take that back. So tiling this forces this. Okay, right? So like that. So there is some positions of placing dominoes force other dominoes, and that is why that's why intuitively that is why this number is expected to be smaller than this number, and indeed it is. We are able to calculate these things exactly because of some magic that we have at our disposal, some machinery that we have at our disposal. Okay, now let me do what a random tiling is here, and unlike the previous rectangle case, there is really something different going on. So if you remember my random tiling of the rectangle, each region looked the same as any other region. Now I take a very large Aztec diamond. I think this is whatever 50 by 50, 50 whatever. You see, I don't know if you can see it very well. This red is meant to illustrate that these are all horizontal dominoes. So red and green are vertical dominoes. Blue and yellow are horizontal dominoes. And you see there is a random tiling taken. So there's a very large number of such tilings of an Aztec diamond of size 50. One is taken at random, so that all are equally likely to be picked, and yet there is all of these become are vertical. These are horizontal. These are vertical. These are horizontal. This has happened naturally. I did not try to pick such dominoes. I picked a uniformly random domino tiling. Okay, never mind how you can do this. There are ways of doing this, but I'll not go there. This is related to a branch of mathematics called sampling, and there is something called exact sampling. So this is exactly random, whatever that means. Okay. There is no bias, I want to assure you. I did not me, because as I said, all the figures are taken from the internet. Whoever did this simulation did not try to do something artificial. This came up spontaneously. Okay. And another thing you can notice is there seems to be some kind of line which is going like that. You see, there's something funny is going on. This line is moving. Okay, so this is how a large random domino tiling, sorry, a domino tiling of a large asteroid diamond looks like. So this is related to something called the Arctic Circle phenomenon. So here is what it is. So as I said, you took a look at a typical tiling, which is what is a random tiling, and then the amazing thing, as in this previous example, is as the size becomes larger and larger, things become less and less random, as opposed to more and more random. And in particular, what will happen? So let me explain directly on this figure, is that this region, when n is, let's say, 1,000,000, it's almost a certainty that this region over here will become tiled by vertical tilings, and similarly these two by horizontal and this by vertical. It's almost a certainty, and there will be a region, there will be a curve separating that from this region inside here, which looks disordered, which looks roughly like the random tiling of a rectangle. You know, so if I look at some small region here, it will look kind of like the domino tiling of the rectangle. Okay. So there is this region which is kind of disordered, and there's this regions outside which are very ordered, and there's going to be this curve that separates both of them. That's what I was trying to point. So there are two kinds of analogies which people have used to describe this. One is the analogy with our regular phases of matter. So as you might know, solids have regular structures, so you can think of this as a solid region. And gases are, all over the place, they are disordered, so you can think of this as a gas, and you can think of the liquid region as separating the two. You can also use an analogy from geology of the Earth. So you have the frozen region, the ice region in the poles, so that's in the extremities, where everything is icy and ordered and nicely stacked. And then you have the tropical region where it's all a mess, and you have the temperate region which separates the two. So these are two analogies. So as I said, frozen region or the Arctic region, and the curve which separates the two is called the Arctic Circle. So in this case, it turns out that in the limit, when you take n very, very large, it will look like this. So the curve separating the two will actually be a circle. Okay, and a circle has more symmetry than a square, which you started out with, but that's how it happens. Okay, so there's a lot of nice and rich mathematics going on, and Andrei Okunkov won the Fields Medal in 2006. Part of his work was to explain these results and to relate them in more advanced topics in mathematics, connect them to representation theory and algebraic geometry. So this. So you might have said, why should I study this random looking shape? And it's really deep. I mean, there are wonderful connections to other branches of mathematics. Okay, so I think I'm running out of time. How long do I have? How much more time do I have?
So you have 10, 20 minutes. 10, 15.
20 minutes? Do I have 20 minutes?
Yes, sir, you can take.
Okay. So if I can take 20 minutes, I can tell you about another class of tiling problems. All right. So this is about partitions, related to partitions. So you might have seen partition, or you might not. I mean, it doesn't matter. So let me tell you what it is. So partition of an integer is its representation in terms of positive integer parts. So for example, 5 can be written as 4 plus 1, 3 plus 2, 2 plus 2 plus 1, etc. So in so many ways, 5 can be split up. Okay. Okay, 5 itself is a partition. So you have 1, 2, 3, 4, 5, 6, 7 partitions of 5, and these are the 7th. And of course, you know addition is commutative. So 1 plus 3 plus 1 is the same as 3 plus 1 plus 1. So by convention, we write them in weakly decreasing order. So partition lambda, you write it as lambda 1 comma lambda 2 up to lambda k, where these are weakly decreasing, okay, or non-increasing. Okay, so as you might know, the Hardy-Ramanujan formula is one of the crowning glories of Ramanujan. He gave an exact formula for counting the number of partitions using quite sophisticated number theory. Um, it's an amazing formula because it's not like 2 to the n choose 2 or something like that we saw earlier. It's quite complicated formula, but what his formula does, or what their formula does, is give an answer which is accurate to within an integer. Okay, so if the actual answer is 1 billion and 1, the answer that this formula will predict may be 1 billion and 1.3. Something very, very close. And if my answer is 1 billion and 1, I am willing to accept an error of 1,000, because that's very small in percent, right? If my formula gave me 1 billion and 1,000, that's completely acceptable because it's a small number. But amazingly, Hardy-Ramanujan formula gives such a beautiful formula. Yeah, I mean it gives an answer which is so accurate. Okay, so let me talk about Young diagrams. So I had mentioned this earlier. So a partition can be represented in the following way. You place lambda k, so lambda is the partition, you place lambda k squares in row k aligned so that they are left justified. So look at this example. So 4, 3, 3, 3, 1. So you put 4 squares in the first row, 3 in the second row, third row and fourth row, and 1 in the last row. These are all left justified. Okay, that's called a Young diagram. Now, there's a generalization of partitions which are called plane partitions. So these are 3-dimensional analogs. And here you could have thought of these partitions as placing boxes in a 2-dimensional room such that they are stacked in the corner. Right? Think of this as there's a room here, and these boxes are stacked in one corner. Like that, you think of this, so there's a room, look at it, the room where you're sitting in, it probably has a corner, there are 3 walls meeting at a point, and you want to stack them so that they are maximally pushed inside. Okay? One other way of thinking is that gravity acts in the 1, 1, 1 direction. It acts towards the corner so that everything sticks over there. Okay? So if you have certain number of boxes, you can arrange them in this stacked corner in so many ways. Each one of them gives a plane partition. Okay, I hope that's clear. Now there is another way of viewing plane partitions, which is in terms of tilings, and this is a modern view on plane partitions. So you take now. So now we are going to do another class of tilings. So far we have been talking about domino tilings. Now I'm going to do another class of tilings. So dominoes, you took a square lattice. You took a rectangle made of unit squares. Now we will make hexagons built up of unit triangles. So there are 2 kinds of triangles, left facing and right facing. Yeah. Okay. Now, the analog of a domino is going to be what is called a lozenge, and a lozenge will be 2 consecutive cells in this triangular lattice. So, so these are the lozenges. So there are 2 consecutive triangles. So let me come back here. So if I take these 2. I get 1 lozenge. If I take those 2, I get a horizontal facing lozenge, and if I take these 2, I get another. So even though there are only 2 kinds of triangles, there are 3 kinds of lozenges, And now if you take this hexagon, this whatever regular hexagon, and you can tile it with the lozenges. Okay, you might have seen domino tilings before, but I'm almost certain you would not have seen lozenge tiling before. And now the amazing thing is, every such tiling, here is an example of a tiling of not that hexagon, but an irregular hexagon, 3 by 3 by 2. So 3 height 3, length 3 and width 2. Your mind automatically interprets this as a plane partition. This is not a plane partition. This is a lozenge tiling. You can see this thing over there is that. This thing over there is that, and this thing over there is on top. So these lozenges remind you of the top of the plane partition. I mean, as you know, this is the problem of perspective, right? Your mind automatically converts this, so it messes up your mind sometimes, because do you want to think of this as the floor or the ceiling, and yeah. So anyway, you might see this as moving also. I mean, your mind switches between both interpretations. Okay, so the modern viewpoint. So what's the upshot? You can think of a plane partition in a room, in a let's say A by B by C room, as a lozenge tiling of an A by B by C hexagon. So the hexagon has to be of the form A B C A B C. Okay, it has to repeat. So here are the lozenge tilings of a all lozenge tilings of a 2 by 2 by 2 room. So ignore this third side. You can also, these two are the same essentially. So look at this. This is an empty room. There's no plane partition here, which is the same as saying that the left half of the or left 1/3, top left 1/3 of the hexagon of a 2 by 2 by 2 hexagon is tiled with this kind of tilings. Top right is tiled by these kind of lozenges, and bottom is tiled bottom 1/3 by these kind of lozenges. Okay, like that. So here, this you can think of as the empty room. This you can think of as tiling with one box, which is again a plane partition. You can maybe see it easier here as a plane partition. The shading makes it worse. I mean, makes it worse in the sense, helps your mind think of it as a three-dimensional object. But all of these are really lozenge tilings. Okay. So they are arranged as follows. The ith row contains I boxes from the plane partition point of view, starting with I equal to 0 and going up to I equal to 8. And there are a total of 20 of them. Okay, any questions? Okay, yeah, please ask if there are any questions. Okay, so I'm not asking, okay, so let me clarify that I am not looking at the number of plane partitions of a given integer. I am looking at number of ways of having plane partitions inside a room, which starts with the all empty, with the empty room with no boxes, all the way up to the full room with all cells, all boxes occupied. Okay, I hope that's clear. And there are 20 possibilities. And so here are all possible ways of having 4 boxes. You can have all 4 at the bottom, all 4 on the right, all 4 on the left, or this symmetric kind of arrangement. Okay. So amazingly, there is an exact formula for this also, and this was due to Percy McMahon, who was actually he was in the English army, and he was posted in India for about 5 years. And after he left the army, he said, okay, I don't want to do all this nonsense, I want to do maths. So he became a mathematician, and so he worked in algebra, number theory and combinatorics, and in fact he published this 2-volume work called Combinatory Analysis, and that was one of the first books on combinatorics, which kind of, you know, elevated it from being like a recreational math field to, you know, true branch of math. Okay, so let M of ABC be the number of plane partitions inside an A by B by C box. As I said, everything from the empty plane partition to the full plane partition. And so McMahon proved this amazing formula for MABC. So it's a triple product. I goes from 1 to A, J goes from 1 to B, K goes from 1 to C. I plus J plus K minus 1 by I plus J plus K minus 2. Okay, really beautiful formula. And as you can see from here, there will be lots of cancellations, right? So there will be some telescopic cancellation, no matter which way you write it. And this is the most symmetric way of writing it. There are other ways which are more compact, but there's no real way of writing it so that it's obvious that this is an integer. I mean, there'll always be some natural denominator, but it is an integer. Okay. And you can see that there's no problem with the denominator because I, J, K are at least 1. So the denominator is at least 1. Okay, another beautiful formula. And again, a reason why you should study this. Now, you can also have just like, okay, I mentioned symmetries of tilings. So let's look at classes of symmetric tilings here. So suppose I now don't want to count all the tilings. I only want to count the tilings in the room which are symmetric about the vertical axis. Okay, so this is an example of a tiling which is symmetric about the vertical axis. So is this. This is not, neither is this. This one is, the full one is, the empty one is, like that. So there are a certain number of symmetric tilings. Another thing you could do is rotate the whole thing by 180 degrees. 120 degrees. Okay, you have a symmetry about rotation by 120, and then, for example, this will remain invariant. So will this, but this which was vertically symmetric will become this when rotation. And that will become this, and then that will become this again by rotation. But there will be some which are invariant under rotation. So, for example, this will be invariant, right? So one can consider various classes of symmetries, and it turns out amazingly that counting the number of tilings which respect those symmetries again has beautiful product formulas like this. Again has very nice product formulas. Some of them were proven only as late as the 70s. So, you know, this McMahon proved this formula maybe in the 1910s, but it took a long time to prove some of these other formulas. Okay. Again, so now what is a typical random tiling of a large n by n by n hexagon look like? Here is an example. I think this is size 60 or something. Oh no, size 20 maybe. Oh. And you see, again, there is the same frozen phenomenon. So, as I said, just like in the Aztec diamond case, no effort had been made to make anything special on the boundary. But it turns out that these corner regions become more and more likely to be frozen. So the red are the vertical dominoes, the green ones are one kind of oblique dominoes, and the blue ones are the other ones, and they become frozen. And so there are these frozen regions, and there are these disordered regions in the middle, and there will be a curve separating the two. And amazingly, even for the hexagon, this curve in the limit, as you make n as you let n go to infinity, this curve will again become a circle. So again, you will have the optic circle phenomenon. Okay, so that's a deep theorem again. So as I was mentioning Okunkov's result, So it turns out that one can, what the work of Okunkov and his collaborators, they were able to construct tilings not only of the hexagon but of more complicated regions. So for example, they took a region like this and did the tiling, and then again you take a random tiling of this region, and you will see some frozen regions here and here and here, the corners. So this is not even convex, right? So, but still you will have nice things, and their theorems guarantee that there will be an Arctic circle, Arctic curve separating the disordered region in the middle from the frozen region outside. And this curve in this case is a cardioid, which is this heart-shaped curve. But in general, they give a prescription for how to find this curve. So that's one of their beautiful results. Okay, so I think I have given you 3 classes of tiling examples, and to show you that these really lead to deep mathematics. They they they, they straddle very abstract regions from algebraic geometry to very concrete regions like combinatorics, concrete branches like combinatorics and probability. And so I hope this motivates you into thinking about mathematics as something beautiful and something worth studying. With that, I thank you for your attention.
Thank you so much, sir. That was a wonderful talk. If there are any questions, the participants may unmute and ask.
Okay, so there one question by Inesh I already answered. I think if you are still there, you want me to clarify, please let me know.
Sir, can you tell me what's the degree of freedom? And I couldn't understand that part.
Oh, okay, so let me go back to the rectangle example. So you remember this formula, right? F of 2 into n, whatever it was.
Yes, sir.
So I'm saying now this is purely a function of n, right? So it's some complicated function of n, but when n is very large, I claim it can be written, just a second. I claim it can be written as some constant raised to the 4n squared. And why 4n squared? Because there are exactly 4n squared small cells in this 2n by 2n squared. Right? It has
For
area
2n by 2n, can we say it is c raised to the power 4 mn?
Yeah, if it was right. If for f2mn, I would have said c to the 4mn.
That means the area.
Area, exactly. But more, yeah, area, but also the number of cells, number of unit squares.
Yes, sir.
Okay. So what does this mean? It means c times c times c 4n squared times. Right? That's by definition.
Yes, sir.
So what this says is this associates a numerical quantity, this number, per cell. So you can think of this f as giving a numerical quantity, which I said degree of freedom, but you can also think of as ease of tiling. Okay, and this number depends on the problem. So in this rectangle problem, we had 1.385, and in the Aztec diamond problem, where did it go? You had 1.189. Okay, I mean in each case that's the object is a cell, a unit square, but the number depends on where it is sitting. It's sitting inside an Aztec diamond or it's sitting inside a rectangle. Okay, so a smaller number means harder to type. Larger number means easier to type. That's what it means. I mean, these are all rough things. I mean, if one wants to say it precisely, one needs a little more terminology, and that's what I'm not getting into. But there is a way to make these things precise. Okay, and it means something.
Do we define C to be the degree of freedom, or it is just a derivation that C comes out to be the degree of freedom?
No, I'm saying this is the definition of degree of freedom. So you write your formula as C raised to the number of squares.
Okay, then we define C to be the degree of freedom.
Yes. So in the Aztec diamond example, this was the exact formula, remember? And,
yes, sir.
And I'm writing it as C raised to whatever number of squares, which I calculated to be 2n. So therefore, by definition, C is 2 to the 1/4.
Yes.
Okay,
Sir.
this is what I'm defining C to be. Defining the degree of freedom to be. But I should emphasize, degree of freedom is an English phrase that I'm using loosely. I'm not defining formally what a degree of freedom is or any such thing. I'm just saying roughly what should your intuition be. Okay. 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 I don't think there are any questions.
If there are no more questions, then we may end the meeting. Sunshine.
Yeah. If
Thank
there are
you,
no
sir.
further questions. Thank you, sir. Again.
Okay. Yeah. So, yeah. All right. Thanks. Bye.
Thank you, sir.
Thank you, sir.
Sure. Yeah.
Thank you, sir.
You're welcome.
Thank you, sir.